Okay, so the problem that we're going to work on is number 3 on this, and it says during a rodeo, a clown runs 8 meters north and then turns and runs 3.5 meters at an angle of 35 degrees north of east, and then turns and runs 5 meters parallel to east. And the question says, what is the magnitude and the direction of the clown's displacement? Okay, so I'm going to use some different colors. So first the clown runs 8 meters north, and then he turns and runs 35 meters at an angle 35 degrees north of east. And then he runs 5 meters parallel to east. Okay. So first thing, very first thing is make sure you know north, south, east, and west. Right? So first we run 8 meters north, or the clown runs 8 meters north. And this is just a sketch. I'm not using it to scale. We'll do a to scale picture after this. So now that our clown is here, he goes north of east. So east is this direction, north of east is this way, and he goes at an angle of 35 degrees north of east, and it says he goes 3.5 meters. And then he runs parallel to east 5 meters. And anytime you have a vector problem like this, you're really doing 3 things, and we've already done the first major step. So the first major step is to draw a picture. Which we've done. The second major step is to make right triangles. We know that our rodeo clown's displacement is from start to finish in a straight line. So this is our rodeo, this is the displacement. Sometimes it'll also say resultant displacement. Those are both the same thing. But right now you're saying, oh, that doesn't look like a right triangle, right? So anytime, don't freak out if you don't automatically see the right triangles. The most common way you're going to make the right triangles is by extending the So the most common way to make right triangles is by extending the vertical and horizontal lines. We have one there and one there. And that makes a nice big right triangle. It also makes another little right triangle. So the next step, once we've got our triangles, we need to create components. So our third step will be to calculate components. So components, remember, are parts of our vectors, especially if they're going off at an angle like this one, right? So this one, our first vector in bright green, is 8 meters north. So we don't need to calculate the components of that because all of it is north. This one, we need to know how much it went north and how much it went east so that we can fill out the sides of our big right triangle. Okay. And then this one, same thing. We don't necessarily need to worry about it because it is going along our coordinate system, right? We have north, south, east, west. This is only east. This is only north, so we don't need to worry about those. We need to go worry about the ones that are at angles. So, now this one, I'm going to add some more lines here because especially the way I drew it, it's like, okay, I see my triangle, but I don't know how to calculate the components with this triangle because my angle is outside of that triangle. So there's two things you can do. You can either remember that in geometry, if you have two parallel lines that make a Z, the inside angles are the same. So we know that the 35 degrees that's over here is the same as that angle there. That's one thing we could do. Or, and it just depends on which way your brain prefers, or you can make the triangle go inside, right? Because if you have a rectangle like this, so I've got a 3x4 rectangle. If we cut it in half, this side has the same length as this side, and this side has the same length side as this side, right? It just depends on which way your brain prefers. If you want to just leave this triangle here and add in the angle, that's fine. If you want to be like, okay, I know what this side is and I know what that side is, you will get the same results no matter which way you calculate it. So, we need to find some y component and some x component. And remember we use y for math. Just like in math, y is for vertical, x is for horizontal. So, we have an angle, and we know the length of the hypotenuse, right? So if this is a right triangle, we know the hypotenuse. So if we have an angle and a hypotenuse, we need to use trig. Now I just said we have the hypotenuse, right? This is the hypotenuse of our small right triangle. So that means we're going to be using sine and cosine. We won't use tangent because we don't have the opposite or the adjacent side. We just have the hypotenuse and an angle. Alright, so to calculate the horizontal component, is the horizontal component adjacent to our angle or is it opposite from our angle? It's adjacent. So we know cosine of the angle equals the adjacent side divided by the hypotenuse. But this isn't so helpful, right? We need to do something else to this. So we need to make sure we can solve for just the adjacent side. So how do we get the adjacent side by itself? We've got adjacent divided by hypotenuse, so we want to undo that division. What undoes division? Multiply. So multiply by hypotenuse. So this is a really useful way to think about, especially in physics, just kind of, in physics we rarely use this version of sine. Most of the time we use this, right? The adjacent side equals the hypotenuse times cosine of our angle. So with it like in this format, we know the hypotenuse is 3.5 cosine, and our angle is 35 degrees. Anytime you're dealing with trig functions, sine, cosine, tangent, it's always good to make sure you're in degree mode, no matter what calculator you have. If you have a TI-84 or something similar to TI-83, you press the mode button. If you have a TI Inspire, it's up in the corner. Okay, so we have 3.5 times cosine of 35. So this is 2.867. The more decimals you keep until the very end, the better. And this was our adjacent side, this is x. So I'm going to write down on my little picture how much this side is. That way, if I need to come back to it later, I've got it written down. Ta-da! Everything's there. Oh man. Oh well. I'll go back and do a voiceover or something. Something. Oh my god. Splice it in or something like that. Oh well. Here we go. Continuing on. So at this point in time, it depends which side we choose to be the opposite side and which side we choose to be the adjacent side. Because we can measure two different angles. We can measure the angle, this would be north of east. We can also measure his displacement from this angle east of north. And it just depends on which side we're picking to be our opposite side and which side is our adjacent side. And both are correct. Both can be correct. Right? Just like before where we said we could draw a whole rectangle. So just like over here, when we could make our, rather than having it be the outside triangle, we could have the inside triangle. In a similar way, we could decide, okay, I want to find this angle, so this side is my opposite side, right? Which would make either one of those the opposite side. Or we could say, I want to find this angle, and then this is the opposite side, or this is the opposite side, because they're the same thing, right? In the same way, either one could be correct. And that's okay. One trick with these is they should always add up to be what? So whether you find this one or this one, they should always add up to be not the same, but 90 degrees, right? So if you find one and you're not sure if it's correct, and then you flip it around and you find the other, then they should add up to be 90 degrees. And I know with the multiple choice questions, This one might not be on there, but this one is. Right? So it's a little disconcerting. It's like, oh, I don't see my answer. It must be completely wrong. No, it might not be completely wrong. It's just, as teachers, we might be narrowing it down to just make you pick one to make it easier to grade. So, let's find this one. I'm going to start with that one. So, if we find this angle, what's our opposite side? Whatever this y was, right? So that means 10.008 is our opposite side. And then if we're finding this angle, what's the adjacent side? Not 2.867 because that's too small. It's this whole thing, which is 2.867 plus 5, which was 7.865. So we got, and on the TIs, on the TI-84s, they have sine, cosine, tangent. Inverse, sine, inverse, cosine, inverse, tangent are the blue buttons, or the little blue. So inverse tangent of 10.008 divided by 7.865. So this is 51.84 degrees, and this one is north of east. So that means the other one should be how much? So this angle should be so this one should be 38.2 degrees east of north. Right? East of north. So that's the long way to do it. That's the hard way to do it. There's an easier way to do it if you've got a protractor. So I'm going to show you how to do it with the protractor now.
Your recorder. Can you please come to the vestibule and save your recorder?
So going through this whole thing took, and we did go a little slower because I was making sure to pause and explain and write things down. So that one took about 15 minutes, a little bit more than, no, probably more like 20, 25 minutes, including the gap. But if you've got a protractor, let's time it. See how it does. I'm curious. Right. So if we're going to use a protractor, it's still good to draw a little sketch of what we did or what our object did, just so that we know how our picture is going to go. So we go up and then over again. So that means for our paper we might want to start down in this corner. That way we know we're not going to run off the page. So we still want like sketch and choose a scale. So for this one, we have distances of 8 meters, 3.5 meters, 5 meters. What can we use? If you have graph paper, you can always use the squares. If you don't have graph paper, that's okay. You don't have to. And the bigger, the better. So I could use centimeters for this and just use all centimeters. But I could also use inches. Because, and if I use inches, it's going to give us a bigger picture, which in the end is more accurate, because then you can be more precise, right? It's hard to be accurate if you're trying to squeeze everything into a little tiny picture. So the bigger the better. So for this example, I'm going to use 1 meter equals 1 inch. There is another issue with inches, and it comes down to how inches are usually split. So for centimeters, all of these are like 0.1, 0.2, 0.3. This one is not 0.1. This is not 0.2. This is like half. This is a quarter. That's an eighth. That's a 16th. And off the top of my head, I don't know what those are in decimals. So it makes it a little funky, but we'll be okay for this one. So first thing we need to do is go 8. If I'm doing inches, I need to turn my paper this way. So I'm going to change it so that north is this way, because otherwise I would run off the paper, and I don't want to do that. So I'm going to start over here. So here's 6 inches. Start here. Go 6 inches. Here. And then I'll go 2 more. Alright, so 6, 7, 8. And then, actually, never mind. I'm going to go ahead and use centimeter. Change my mind. So, 1, choose scale. 1 centimeter equals 1 meter. Do it that way. So first thing our rodeo clown did was he went 8 meters north. So if 1 centimeter is 1 meter, then I go 8 centimeters like that. This is 8 meters. Next thing he did was he went at an angle of 35 degrees north of east. So here's east, right? So I have to line up my protractor right there. And 35 degrees is going to be here if we're going north of east. I like to draw 2 dots so that I've got more dots to line up. And we're just going to draw a nice big line, and then we're going to make it shorter for the next part. So now we're going to measure and make sure it's the right length. And our rodeo clown went 3.5 meters, so that's to there. So, if we were matching colors from before. So that was bright green, this was dark green, just to match the same colors. And then he went 5 meters directly east. There. And now that our drawing is to scale, we don't have to do a single bit of calculation. All we have to do is measure. So we've got this here. Okay. So that's still our resultant, just like before. And now we need to measure. So that's 10 centimeters there. And then that's 12.5. It looks like my ruler is showing it that it goes to it looks like it's going right to like 12.65 or something like that, or 12, or what did we calculate it to be? 12.7. So there is a little margin of error for the pictures. If your teacher wants it to be super accurate, then you have to make sure that you do the calculations rather than using a protractor. But I'm okay if you're using a protractor in my class. I would recommend that if you think you want to do engineering or some other physical science like physics or astronomy, to actually do the calculations, because that will be what your professor expects in college. But again, we weren't quite done, right? So now we still need to find an angle. So same thing. We just line up our protractor right here. Make sure everything's nice and square. So that's a nice thing about using grid paper. You can make it nice and lined up. So this one looks like 50, that's 51, 52. So somewhere between 51 and 52. Maybe more like 52. And what did we calculate this one to be? Like 51.8. Right? So that's still also really close. But what if you wanted to do this one instead? What do? Same thing. You still line up your protractor. Notice I'm switching sides simply because I think it would be easier to try and measure. Yeah, so rather than using 90 to whatever, I don't want to do that. I want to start from 0. So I'm just turning my protractor to make it more convenient. And this one we said was supposed to be 30 something, 38. Looks like it's somewhere between 37 and 38. And that took us all of like 10 minutes. So like half the time. And again, that was because I was stopping and explaining and all sorts of things like that. So with practice, this way is a lot quicker. 'Cause look at all that. Right, we've got all of that versus just that.